So for this subject extension, I've just chosen a parametric question which has differentiation, and it has converting parametrics to Cartesian, and there's an integration there at the end. These are covered in your EPA topics that you'll be assessed on at the end of the year. So differentiation and integration does include parametrics potentially. It's certainly in those chapters, so it's worth looking at. So we've got here a curve which has parametric equations given, x equals 1 over t and y equals 1 over 1 plus t and y equals 1 over 1 minus t, where t is in between minus 1 and 1. And we're asked to find the equation of a tangent. So, we know that whenever we're asked to find the equation of a tangent, we're going to have to differentiate, okay? So when we differentiate parametrics, the way that we work is by saying that dy by dx, because that's what we're after, has to be differentiated in terms of this third parameter, t. And we use the same ideas as we implement when we use connected rates of change. So we can split this dy by dx up into the product of two differentials, where the unknown here on the bottom of this one and the top of this one is going to be dt, because it's t that's our third parameter that we're working with. So if we know that dy by dx is dy by dt multiplied by dt by dx, we can go ahead and work from there. Now, ordinarily, we'd write this as dy by dt and then divided by dx by dt. Now, this question is a bit interesting because of these reciprocal functions, but that's the principle, okay? That's how we differentiate parametric equations. So we do need to find dx by dt. We need to differentiate that. We also need to find dy by dt, and then we use those two together. So if we look at the question, x equals 1 over 1 plus t, that's the same as saying, say, x equals 1 plus t to the minus 1. So that's how we're going to differentiate it. So dx by dt then becomes minus 1 plus t to the minus 2, which of course is minus 1 over 1 plus t squared. Similarly, we've got y is 1 over 1 minus t, which is the same as 1 minus t to the minus 1, and that's what we're going to differentiate. And so if we do that, so it's not minus, my apologies. I put the minus in for some reason there. So there's no minus there. Oh no, yeah, sorry. There is a minus there because it's dx by dt. And then dy by dt, we just differentiate here. So we get minus multiplied, so we've got minus 1 minus t to the minus 2, and then multiplied by the minus 1, which is what we get when we differentiate the bracket, which is just going to be 1 over 1 minus t squared. So then we work out dy by dx. And dy by dx, we would normally use dy by dt divided by dx by dt. Well, that is what we're going to do, so let's just go for it and do that. So dy by dt is 1 over 1 minus t squared, and we're going to divide that by dx by dt, which is minus 1 over 1 plus t squared. So that's the dy by dt, and that's dx by dt. And then we simplify that down, then we end up with minus 1 plus t squared over 1 minus t squared. Okay, because it's like saying it's this fraction multiplied by the reciprocal of that fraction. So you'd have to imagine it being this multiplied by this upside down. So 1 plus t squared over 1 minus. And that's what we do. Okay. Did I get that the right way around? Hang on. Yeah. Yes, that's absolutely right. So we've got our dy by dx, and then we just want to work out what the value of the gradient is at that point. So at t equals 1/2, dy by dx is going to be equal to, let's substitute a half into here. So we've got minus 3 over 2 squared divided by 1 minus a half, so we've got a half squared, which is minus 9 over 4 divided by 1 over 4, which is minus 9. So that's our gradient of our tangent, all right? So we've worked out dy by dx. We have substituted t equals a half. We now have a value of the gradient of the tangent at that point. We need to now use the conversion formula, y minus y1 equals mx minus x1, which gives us our equation of a line. In order for that to work, we need m, which we've got. We need a y, and we need an x. So we need to do a bit more work. At t equals a half, we can work out what x equals by substituting into this equation 1 over 1 plus t. So where t is a half, 1 plus t is 3 over 2. 1 over 3 over 2 is 2/3. And y is going to be given when we substitute t into the second equation here. So we get y by doing 1 minus a half, which is a half. 1 divided by a half is 2. So now we have all the elements in place, we can just substitute our values. So y minus 2 equals minus 9 brackets x minus 2/3. And then we can expand and simplify. Y minus 2 equals minus 9x plus 6. And we just get y equals minus 9x 6 plus 2 plus 8. And that's our equation of a tangent. All right. Now the processes there are the same for every differentiation question. Find dy by dx, find the gradient, use y minus y1 equals mx minus x1, and you're done. The added complication with parametrics is we need to take care over our dy by dx and remember to use t. And once we've got that, we'll generally be given a t value to substitute in. And then we're going to have to work out our coordinates x and y based on that t value. But then the process is the same. So there is a part B and a part C to this question. Part B, we're asked to show that C satisfies this Cartesian equation. So we need to use our x equals 1 over 1 plus t and y equals 1 over 1 minus t, where t is between minus 1 and 1. And what we're looking to do is to rearrange these, put them together simultaneously and get this equation. Now the most effective way to do that is to rearrange your x equation and substitute into your y equation, because then you're going to get y equals something to do with x. So to rearrange the x equation, I'm going to do x multiplied by 1 plus t as 1, multiply both sides there by 1 plus t. I will expand the bracket, because what I'm trying to do here is I'm trying to get t on its own in terms of x, so I can substitute in here. So xt equals 1 minus x, which means that t equals 1 minus x divided by x. Now I could simplify this a little further, but actually I'm going to substitute it in as I see it. So that means that y equals 1 over 1 minus this fraction, 1 minus x over x. And you can already see we have an equation purely in terms of y and x, which is what we're after. Let's simplify this down a little bit. This 1 I'm going to think of as x over x, so that I can combine this 1 with this fraction. So you can see 1 minus this fraction. And then I'll simplify further, and I'll say, well, x minus 1 minus x is 2x minus 1 divided by x. All right, that's combining these two fractions together, just using fraction arithmetic. And if we're doing 1 over this fraction, then we've got x over 2x plus minus 1, which is as required. So now we get into a little bit of integration, and we've actually got a number of options here to use for integration. We could integrate the parametrics. Okay, we could integrate the parametric using this y times dx by dt. We could do that. I think that's possibly a more complicated way of doing things, so I'm going to ignore that for now. We could rearrange, or sorry, we could rewrite this x over 2x minus 1 as a different fraction to do with x that we can integrate, because we can't, in a way, integrate it at the moment. Or we could use parts, or we could use substitution. And my preference here is actually substitution. So for part C, we're being asked to integrate between 2/3 and 1, and that space there, so between 2/3 and 1, this fraction x over 2x minus 1 dx. Okay, that's our goal. So I've said that I'm going to use a substitution, because, and the reason is because x over 2x minus 1 doesn't fall into any of our normal categories for integration, so we have to think outside the box a little bit. And I'm going to use the substitution u equals 2x minus 1. All right. Now the reason I've chosen that is it gets rid of this whole denominator and just shrinks it into u. Now what we have to do with this is I need x equals something, because I need to replace this x. I've already replaced 2x minus 1. I need to replace x. So I'm going to say that u plus 1 over 2 is x. So I've got my x done. I've got my 2x minus 1 done. Now I need to replace dx. So to do that, I differentiate my substitution u, and du by dx equals 2, which means that du is 2 dx, which means that dx is half u. So now I've got this ready to substitute, this ready to substitute, and this ready to substitute. And the only thing I need to think about now are my limits, because my limits currently are in terms of x, and I need them in terms of u. So I'll say at x equals 2/3, my lower limit, u equals, and we substitute x equal into here to find out what u is. 2 times 2/3 is 4/3, minus 1 is 1/3, so we have u as 1/3. At x equals 1, u equals 2 times 1 minus 1, which is 1. So my integral then becomes, so I'll do there's the integral I started with. We've changed that into 1/3 to 1 using our u values here. And then we're going to have, right, x divided by, so x was u plus 1 over 2. That's our x, divided by 2x minus 1, that's our u. And then dx, which is 1/2 du. Which looks a lot more complicated, but shrinks down quite nicely. So if we've got u plus 1 divided by 2, so that, I mean, I'll put in as many lines of working as I can here. That's the same as saying that. So we multiply by 1/2 du, which is the same as u plus 1 over 4u du. All right, so just shrunk that down bit by bit. The 2, when I divide that by 2, then it becomes part of the denominator, and then this 2 here goes in part of the denominator as well. And then even further, just to make life even simpler, I'll take 1/4 out as a fraction. And I've got u plus 1 over u. Now it's not quite ready to integrate. The final thing I'm going to do here is just to say u plus 1 over 2 is exactly the same as 1 plus 1 over u. Those two things are the same. In case you're wondering why, u plus 1 over u is the same as u over u plus 1 over u. Okay? So now we're ready to actually go ahead and integrate. So 1/4 of this integral, 1 plus 1 over u du, is equal to 1/4, and then we'll do our integral. So we've got u plus natural log of u between 1/3 and 1. Okay. And then we'll substitute. So we've got 1/4, we've got 1 plus natural log of 1 is 0. We substitute our third. We have a third plus natural log of a third. Now, natural log of a third, we can simplify, because natural log of a third is the same as natural log of 3 to the minus 1, which is the same as minus natural log of 3. Okay, so I'm going to use this version in here. It's a very handy thing to be able to do because we're dealing primarily with exact values. So 1 plus 0 is 1. We've got minus 1/3, and then minus log 3, because the log third, so adding log third becomes taking away log 3. So we're subtracting minus log 3, so we have plus log 3. And then we're almost there. So we've got a quarter. 1 minus a third is 2/3 plus my log 3. And so what we have then is 1/6 plus 1/4 log 3, which is exactly what the question asked us to do, to write it in the form a plus b log c. So for that last part, like I said, you could have done it using parametric integration using the t. You could have done it by parts. You could have done it by splitting the fraction x over 2x minus 1 up further into something simpler, or you could do it the way I did it using substitution. Anyway, you should get the same result. Okay, so that's that. Quite an involved question, but straightforward if you know your processes.